In the previous subtopic, we discussed electric current and electric current in conductors. In this subtopic, we are going to discuss drift of electrons and the origin of resistivity. We are also going to discuss about mobility. What can you see here on the slide? Yes, it's a copper strip and a bulb. What do you know about a copper strip and a bulb? Is it a conductor? You're right. It's a conductor. What do you know about conductors? Do they have free electrons moving inside them? Yes. Copper strip and tungsten filament here are both conductors. So they have free electrons moving inside them. Now let me ask you a few questions. Does current flow through this copper strip and bulb shown in the figure? Will you get a shock if you touch it? What will be your answer to these two questions? You are absolutely right. You will say no. Why don't we get a shock if we touch a copper strip or a bulb, even though there are free electrons moving inside them? What do you know about isolated metallic conductors? Now in this figure, you can see an isolated metallic conductor. So when we say isolated metallic conductor, we know that there is no electric field present across the conductor. The two ends of the conductor are at the same potential. Now what can you see here inside an isolated metallic conductor? You're right. There are free electrons moving inside the isolated metallic conductor, but they are all moving in random directions. What can you see here? For every electron moving in a particular direction, right? There is another electron moving exactly opposite to that, and as a result, the effect will be nullified. So what will happen to all the thermal velocities if I sum up the thermal velocities of the free electrons moving inside the metallic conductor? Definitely the sum of all the thermal velocities inside the isolated metallic conductor will sum up to 0. So did you get your answer now? Why we don't have current flowing through a conductor that is in an isolated state? Okay. Now what can you see here in this particular slide? What is done to the same bulb? We can see a battery connected across this bulb. What happens to the same bulb now if we connect a battery across it? What causes the charges to move? Do the charges follow any particular direction when they move? Do the moving charges now constitute a continuous current? So these are the questions that will come in your mind. So in this subtopic, drift of electrons and the origin of resistivity, you will be able to answer all these questions. What can you see in the figure here? What is applied across the conductor? Yes, there is a potential difference applied across this conductor. What is experienced by the conductor due to the potential difference applied across it? An electric field. What is the direction of this electric field? You are absolutely right. It is from the positive potential end to the negative potential end as shown in this figure. What is the speed of the electric field? The electric field moves as fast as the speed of light, that is 3 into 10 to the power 8 meters per second. Do the free electrons now experience a force due to the presence of this electric field? Definitely yes. It experiences an electrostatic force equal to the charge times the electric field. Do the free electrons still move in random directions now? No, they will now head towards the positive potential end as shown in the figure. So we see that the electrons are now accelerated and drifted towards the positive potential end. What else can you see inside the conductor rather than the free electrons? Yes, there are metal ions. Will the moving electrons undergo collisions with the metal ions? Definitely yes. The metal ions are like huge hurdles in their path. The collision of the electron do not occur at regular times but at random times. This time span for which the electron moves freely inside the conductor under the influence of an external electric field before it undergoes collision with the positive ions is called the relaxation time. The velocity acquired by the electron will be the acceleration times the relaxation time as shown in this equation. What is the acceleration acquired by the electrons? The acceleration acquired by the electrons is given by the ratio of the equation of force to mass, that is minus E into the electric field divided by the mass of the electron. So what is the velocity acquired by each free electron now? The velocity acquired by each free electron will be the sum of the thermal velocity plus the velocity acquired due to the electric field. What will be the average drift velocity of the electrons? To find the average drift velocity, we'll have to take the summation of all the thermal velocities plus the velocities acquired due to the electric field and divide it by the total number of free electrons available for conduction. Now we can split this equation into two parts. One for the summation of all the thermal velocities or the average of all the thermal velocities and the average of all the velocities acquired due to the electric field. What do we know about the summation of all the thermal velocities? Yes, the summation of all the thermal velocities is 0. So the equation for average drift velocity is equal to the summation of all the velocities acquired due to the electric field divided by the total number of free electrons available for conduction. Now if we replace the velocity acquired by the electron by this equation, that is the acceleration into the relaxation time, we get the equation as acceleration into the summation of all the relaxation times divided by n, that is the number of free electrons available for conduction. So it is same as finding the average relaxation time in this equation. Therefore, the drift velocity equation reduces to acceleration into tau, that is the average relaxation time. So what will be the equation for drift velocity? If we replace the equation for acceleration in this drift velocity given by the equation for acceleration shown in this particular equation, we get the drift velocity equation as minus the charge of the electron into the electric field into the average relaxation time divided by the mass. What can we say about a negative sign in this particular equation? What does it imply? You're right. It implies that a drift velocity direction and the electric field direction are exactly in the opposite manner. That is, the drift velocity is opposite to the direction of the electric field. Therefore, we can define drift velocity as the average velocity with which the free electrons get drifted towards the positive potential under the effect of the applied field E and is called as the drift velocity. Electrical conductivity. It is the measure of the ability of the conductor to conduct electricity. So let us discuss the relation between drift velocity and conductivity. Consider a cylindrical conductor of area of cross section A. Let D be an elementary length of this cylindrical conductor. If N is a number of charge carriers per unit volume, we can find what are the total number of charge carriers in this elementary volume of length D. So the total mobile charges in length D will be the number of charge carriers per unit volume into the volume of this elementary length. The volume of the elementary length is the area of cross section into the elementary length D. So the total mobile charges in this elementary volume of length D will be N E A into D. If Vd is the drift velocity of these electrons gained under the influence of the electric field that is set up across the conductor, Vd can be obtained from the equation of displacement upon time, where the displacement d is the distance covered by the electrons as they are drifting. So the time from this equation can be obtained as displacement upon the drift velocity. The amount of charge carriers crossing the area of cross section A, the magnitude of current I is given by the ratio of Q by T, that is NEA into Vd. If we replace the drift velocity in this equation for current, we get the equation as Ne squared E tau A upon M. The current density is the current per unit area of cross section. So we get the equation as Ne squared E tau upon M. So the area of cross section in the numerator and denominator will cancel off. The conductivity of the conductor is given by the ratio of current density to the electric field. So we get the equation for conductivity as Ne squared tau upon M. So we see here that the conductivity is directly proportional to the number of charge carriers per unit volume. N is also directly proportional to the relaxation time of the electrons. Mobility. The electron mobility characterizes how quickly an electron can move through a metal or semiconductor when pulled by an electric field. We can define mobility as the value of the drift velocity per unit of electric field strength. What can you see in this picture? You're right. We can see the mobile charges moving inside the conductor. What will happen to these mobile charges with the variation in temperature? Do they also depend on temperature? What will happen to them at lower temperatures? You are absolutely right. The charges will move more slowly. So there is more time for them to interact with charged impurities. As a result, as the temperature decreases, impurity scattering will increase and the mobility here will decrease. The equation for mobility is mu equal to drift velocity upon the electric field strength. If we substitute in this equation for drift velocity, that is charge into the electric field into relaxation time upon the mass of the charge, we get the equation for mobility mu as E into tau upon m, that is the charge into the relaxation time upon the mass of the charge. So we see here that the mobility is directly proportional to the relaxation time. More the relaxation time, more will be the mobility. The SI unit for mobility is centimeters squared per volt second.